Morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube. Good morning. Today I am discussing about centrifugal pump. The hydraulic machine which convert the mechanical energy into hydraulic energy are called pump. The hydraulic energy is in the form of pressure energy if the mechanical energy is converted into pressure energy by means of a centrifugal force acting on the fluid by the hydraulic machine is called centrifugal pump. The centrifugal pump acts as a reverse of an inward flow radial flow reaction turbine. This means that the flow of centrifugal pump is in the radial outward direction. The centrifugal pump works on the principle of forced vortex flow, which means that when a certain mass of the liquid is rotated by an external torque, the rise of pressure head of the rotating liquid takes place. The rise in pressure head at any point of the rotating liquid is proportional to the square of the tangential velocity at the point. Thus, at the inlet of the impeller where radius is more, the rise of pressure head will be more and the liquid will be discharged at the outlet with a high pressure head. Main parts of a centrifugal pump. The following are the main parts of a centrifugal pump: impeller, casing, suction pipe with a foot valve and strainer. Another one is the delivery pipe. Impeller, that is the rotating part of a centrifugal pump, is called impeller. It consists of a series of backward curved vanes. The impeller mounted on a shaft which is connected to the shaft of an electric motor. Casing. The casing of a centrifugal pump is similar to the casing of a reaction turbine. In a airtight passing surrounding the impeller and is designed in such a way that the kinetic energy of the water discharged. Volute casing as shown in figure. Vortex casing as shown in figure and casing with guide plates. Volute casing which surrounds the impeller if it is a spiral type in which area of the flow increases gradually. The increase in area of flow decreases the velocity of flow. The decrease in velocity increases the pressure of the water flowing through the casing. It has been observed that in case of a volute casing, the efficiency of the pump increases slightly as a large amount of energy is lost due to the formation of eddies. Impeller, casing, delivery valve, delivery pipe, suction pipe, sump. Okay. Vortex, main parts of a centrifugal pump. If a circular chamber is introduced between the casing and the impeller as shown in figure, the casing is known as vortex casing. Introducing a circular chamber, the loss of energy due to formation of eddies is reduced to a considerable extent. Thus, the efficiency of the pump is more than the efficiency when only volute casing is provided. Casing with guide plates. This casing is shown in which the impeller is surrounded by a series of guide plates. mounted on a ring which is known as diffuser. The guide vanes are designed suction pipe with a foot valve and strainer, a pipe whose one end is connected to the inlet of the pump and the other end of the pipe other end inlet of the pump, other end pipe dips into the water in a sump is known as suction pipe. A foot valve, which is a non-return valve or one-way type of valve, is fitted at the lower end of the suction pipe. The foot valve opens only in an upward direction. A strainer is also fitted at the lower end of the suction pipe. Delivery pipe, a pipe whose one end is connected to the outlet of the pump, other end delivers the water at required height, is known as delivery pipe. Work done by the centrifugal pump or by impeller on water, in case of the centrifugal pump, work is done by the impeller on the water. The expression for the work done by the impeller on the water is obtained by drawing velocity triangle at the inlet and outlet of the impeller. The water enters the impeller radially inlet for best efficiency of the sump, which means the absolute velocity of water at inlet makes an angle of 90 degree with the direction of motion of the impeller at inlet. Hence, angle alpha equal to 90 degree and VW1 equal to 0. For drawing the velocity triangle, this is the drawing of velocity triangle. One is the inlet, another one is the exit. N is the speed of the impeller in RPM, d1 is the diameter of the impeller at inlet, e1 is the tangential velocity of the impeller at inlet. U is equal to pi d1n by 60. d2 is the diameter of the impeller at outlet. So diameter u2 is equal to tangential velocity of impeller at outlet pi d2n by 60. v1 is equal to absolute velocity of water at inlet. vr1 relative velocity vr1 Vr1, that is the relative velocity of water at inlet, alpha, that is the angle made by absolute velocity v1 at inlet in the direction of motion of vane. So theta, that is the angle made by relative velocity Vr1 at inlet with direction of motion of vane, and v2 as the water enters the impeller radially, which means an absolute velocity of water at inlet is in the radial direction, and hence an angle alpha equal to 90 degree and VW1 equal to 0. A centrifugal pump is the reverse of a radially inward flow reaction turbine, but in case of radially inward flow reaction turbine, the work done per unit time as the water enters impeller radially, which means the absolute velocity of water at inlet is in the radial direction, and hence the angle alpha equal to 90 degree and VW1 equal to 0 degree. A centrifugal pump is the reverse of the radially inward flow reaction turbine, but in case of radially inward flow reaction turbine, the work done by the water on the runner per second per unit weight of the water striking per second is given by 1 by G Vw1 U1 by minus Vw2 U2. Work done by the impeller on the water per second per unit weight striking minus work done in case of turbine. So minus 1 by G Vw1 U1 minus Vw2 U2. So 1 by G Vw2 U2 minus Vw1 U1. So that is equal to 1 by G Vw2 U2. So W is equal to weight of the water, Q is equal to volume of the water, Q is equal to area into velocity of flow, pi d1 v1 into vf1, that is equal to pi d2 into v2 into vf2. So where v1 and v2 are width of the impeller at the inlet and outlet, and vf1 and vf2 are velocities of flow at inlet and outlet. Definition of head. What is the definition of suction head? It is the vertical height of the center line of the centrifugal pump above the water surface in the tank or pump from which water is to be lifted as shown in figure. This height is also called suction lift, denoted by H. Another one is the delivery head. Delivery head, the vertical distance between the center line of the pump and the water surface in the tank to which water is delivered is known as delivery head. This denoted by HD. Static head, the sum of suction head and delivery head is known as static head. This is represented by HS. HS is equal to HS plus HD. Manometric head. The manometric head is defined as the head against which a centrifugal pump has to work. It is denoted by HM. It is given by the following expression. HM is equal to head imparted by the impeller to the water minus loss of head in the pump. So that is equal to Vw2 U2 by G minus loss of head in impeller and casing. Vw2 U2 by G. So if loss of head, loss of pump is 0, HM is equal to total head at outlet of the pump minus total head at the inlet of the pump. So P0 by rho G plus V0 square by 2G plus Z0. Then minus P1 by rho G plus V1 square by 2G plus Z1. So P0 by rho G, pressure head at outlet of the pump HD, V0 square by 2G, velocity head at outlet of the pump, velocity head in delivery pipe, Z0, that is the vertical height of the outlet of the pump from datum. So total head, that is equal to HS plus HD plus HFS plus HFT plus VD square by 2G. HS, that is the suction head, HD, that is the delivery head, HF, that is the frictional head, loss in suction pipe, HFT, that is the frictional head loss in delivery pipe, and VD is the velocity of water in delivery pipe. Efficiencies of a centrifugal pump. In case of centrifugal pump, the power is transmitted from the shaft of the electric motor to the shaft of the pump. Then the impeller, from the impeller, the power is given to the water. Power is decreasing from the shaft to the pump of the impeller, and when to the water, the following are the important characteristics of a centrifugal pump: monometric, manometric efficiency, mechanical efficiency, overall efficiency. Manometric efficiency, the ratio of manometric head to the head imparted by the impeller to the water is known as manometric efficiency. Mathematically, it is written manometric head divided by head imparted by the impeller to the turbine. So, HM, that is equal to HM by VW2U2 by G. GHM VW2U2 by VW2. The power of the impeller of the pump is more than the power given to the water at the outlet pump. The ratio of the power given to water at outlet of the pump to the power available at the impeller, the power of the power to the water outlet at the pump, WHM by 1000 kilowatt. The power at the impeller, work done by impeller per second by 1000. So W by G, VW2U2 by 1000. So W by HM by 1000, W by G, VW2 into U2 by 1000. So that is equal to GHM by VW2U2. Mechanical efficiency, the power at the shaft work of the centrifugal pump is more than the power available at the impeller of the pump. The ratio of the power available at the impeller of the power at the shaft of a centrifugal pump, this is known as mechanical efficiency. It is written as eta m, power at the impeller and power at the shaft. The power at the impeller in kilowatt, work done by impeller per second by 1000, W by G, VW2U2 by 1000. So W by G, VW2U2 by 1000 divided by SP. So overall efficiency, it is defined as the ratio of power output of the pump to the power input to a pump. The power output of the pump in kilowatt, that is equal to WHM by 1000. Okay, WHM by 1000. So power input to the pump, power supply by the electric motor, SP of the pump, WHM by 1000. Eta 0, eta manometric into eta m. Now one numerical problem, the internal and external diameter of the impeller of a centrifugal pump are 200 mm and 400 mm respectively. The pump is running at 1200 rpm. The vane angle of the impeller at the inlet and outlet are 20 degree and 30 degree respectively. The water enters the impeller radially and velocity of the flow is constant. Determine the work done by the impeller per unit weight of water. Now U1, that is the pi d1n by 60. U2, that is the pi d2n by 60. So from inlet velocity triangle, tan theta is equal to Vf1 by Vf2 U1. From outlet velocity tan phi, Vf1 U2 by Vw1. So 4.57, 25.13 minus Vw2. So that is equal to 4.57 tan phi, 4.57 by tan 30 degree, 7.915. Okay. Now the work done per kg of water per second is given by the equation as 1 by G VW2U2. So 17.215 into 25.13 by 9.81, that is equal to 44.1 Newton meter per Newton. Okay, thank you. Last, if you like my video, you have to subscribe. Okay, thank you.